All right, so this video is to go over the notes for today. This is Unit 5, Day 3. Your notes start on page 160, pink pages 160. So just a couple of important dates in case the sub didn't tell you. Your Unit 5 quiz will be April 20th. All late work will be due April 22nd. That includes any missing tests or any technology projects. And then your Unit 5 test will be April 26th, with your final exam for this class being May 4th. Now, if we have had this, I am making these videos in January in preparation for my maternity leave. So if we have had any snow days at all, these dates have changed. Your sub should have accurate dates to tell you in case these dates have changed. So check with them in case we've had any snow days or whatever has happened that may have thrown off the schedule since literally January. But this is what I have to work with right now that I wanted to tell you. Okay, so today we're going to look at, in the warm-up you should have gone over your t-test. So the beginning of this unit, we started looking at our t-tests. They corresponded with those confidence t-intervals that we had done in Unit 4. Well, just like Unit 4, we had those confidence t-intervals, we had z-intervals. The same thing is going to come here with z-test. So our t-test, when we were talking about means and standard deviations, our z-test is when we're looking at proportions or percents. So we did this a lot with our intervals. If we're given a population with a proportion or percent in it, that means we're going to run a z-test instead of a t-test. So just like yesterday, there's two types of tests. If you're given one population, you run a one-prop z-test. If you have two populations, you run a two-prop z-test. So same thing that we did yesterday. And then our same rules apply for writing our null and alternative hypothesis. Remember, we always stick to our null hypothesis being equals when we write it, and then our alternative can be one of those three things, either not equals, less than, or greater than. So we stick to our null always being equals. That's the majority of how statistics is done. So to run, there's not much notes because it's pretty similar to a t-test. Our conditions, just like with our confidence intervals, is going to change a little bit, but we'll go over that in some examples. The only thing that's going to change is the information that we need on our calculator. And again, I think that you'll remember it's a lot of the same things as our confidence intervals when we ran a z interval, a prop z interval. It's just applying it to a hypothesis test instead of a confidence interval. So if you in your notes will go to page 160, we will look at an example together. And hopefully with some examples, it will kind of help you see what I'm talking about. So go ahead and turn to page 160. Kind of in the middle of the page, you should see this example. So it says in a random sample, we're on page 160 still, in a random sample of 250 freshmen, 45% said that they like their school. In a random sample of 320 seniors, this is not the problem we should be doing right now. Sorry, I apologize. This is going to come in when we do two proportions. So I'm going to have you go to page 161. I apologize. I don't know what my numbering was all messed up. I'm going to have you go to page 161 and let's look at that example because the one we're about to do is our two proportion, and not that it's any different, but let's just look at one proportion right now. So at a large university, a study found that 25% of students who commute travel more than 14 miles to campus. With significance level of 0.1, are these findings in support of a sample of 100 students and 30 of them drove more than 14 miles. So remember, we'll need that initial p-value or that initial claim. So our p-naught that we're going to test against is that 25% or 0.25, right? That's the initial That's the initial finding or the initial claim that they're making, and we're going to test against that. So then we did a sample, or we did a study, and we found that out of 100 students, 30 of them drove more than 14 miles. So our X value, or our N value, would be 100. We asked 100 students, and 30 of them, right, X equals 30, 30 of them were part of our sample, or responded to our sample in the way we were looking for. So this is, again, because we're given a proportion, this is a 1 prop Z test. Now these conditions, we go back to our Z interval conditions. They're the same as when we ran prop Z intervals. We need a simple random sample. Our N times P value needs to be greater than or equal to 10. And our N times 1 minus P value needs to be greater than or equal to 10. Remember, if we don't know P off the top of our head, we can take X divided by N, and that will tell us P. So if I take 30 over 100, I get that my P value is 0.3. So if I do 100 times 0.3, I get 30, which is greater than or equal to 10. And if I do 100 times 1 minus 0.3, I would end up with 70, which is also greater than or equal to 10. Okay, so then our last one, this one doesn't change either. From our t-test, yeah, they're really the only different one from a t-test to a prop z-test is that middle, that second condition. We're still going to test that our interval or our N value is not too large. So it's safe to assume that there are more than 100 students on a large university campus, or more than 1,000 students. Sorry, I should have added a 0 here. But it's still safe to assume there are more than 1,000 students on a large university campus. So, we are testing the claim that no more than 25% of the students. This one is a little tricky. This goes back to when we were writing our null and alternative hypothesis. Remember, no more means that our p-value is less than or equal to 0.25. So because that has a quality in it, this is actually our claim. We talked about that a couple times when we talked about our null and alternative hypothesis. So this tells us that p equaling 0.25 is our claim, right? Because our claim has some sort of a quality in it. So then the opposite of this claim, going off of our pairings, is that it's greater than, so we would write that p is greater than 0.25 as our alternative hypothesis. This is the one, and that's that exception, that weird exception to writing our null and alternative hypothesis. So no more than 25% of students who commute travel more than 14 miles to campus. All right, so now it's time to run our prop Z test. So again, it's pretty similar to how we run our t-tests and our prop Z intervals. All right, we're going to hit stats, go over to test, and then we're looking for that one prop Z test, which is number 5. And then we're just going to type in that information that we laid out up here. So our initial p-value is 0.25. Our X is 30, our N is 100, and then our alternative hypothesis is that it is greater than that 0.25. So we'll go ahead and calculate. So our Z value is 1.155. We're testing it against a 0.1 significance level. and we got that our p-value was 0.12. So that is greater than this. So we're going to fail to reject our null hypothesis, right? When our p is low, we reject. When our p is not low, we fail to reject. So we're going to keep this, which means we're supporting our claim that no more than 25% of students who commute travel more than 14 miles. And that's what we'll end up writing. And it's important that we write a thorough conclusion about the test that we just ran so that people can understand, right, what conclusion that we are drawing and if we're supporting or failing to support our claim and what that claim was initially. We want a thorough conclusion in these types of problems. Okay, so let's go ahead and look at another prop Z test, a one prop Z test, and then we'll talk about when we have two samples. So we looked at the example on 161. So let's go ahead and look at the example on 162. If you want to go ahead and pause the video and try this by yourself, see how much of the information that you can fill out on your own, that's a great idea. It's good to kind of test your knowledge and figure out what you know and where your gaps are. If you don't feel comfortable yet, that's fine. We're going to do a ton more examples. So hopefully by the end of this, you'll feel more comfortable. So this is our example on 162. It says a recent article claimed at most 30% of people who have been in a plane crash have died. In a sample of 100 people who have been in a plane crash, 38 died. Is the article statement believable? Use a significance level of 0.5. So the values that we need, right? The initial claim is that it's 30%. So our P naught, or our initial P value that we're testing against, is 30%. And then we ran our own sample of 100 people. So N is 100. We found that 38 of them died. So again, if I want to find my p-value, that will come later when I do my conditions check, I just do x divided by n. So 38 divided by 100 would give me 0.38. Because we're given a proportion and there's only one to go off of, this is going to be a one prop Z test. So then we'll check those same conditions that we checked in our last example. So that we have a simple random sample, and we have a sample, we'll assume it's random in this case. And then we'll test that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So if I do 100 times 0.38, I end up with 38. You should always note that n times p is also just x, so your x value is what you'd get here. So that's good, and then if I do n times 1 minus 0.38, I would end up with 62, which is also greater than or equal to 10. So we're good on that condition, and then our other condition is that our n value is less than 0.1. So we're going to say it's reasonable to assume that there have been more than 1,000 people who have been in a plane crash ever, so that we can go ahead and run this study. So this is going back to our other, right? We talked about the, in our last example, those kind of special exceptions to writing our null and alternative hypothesis, right? It says at most 30% of people. So we can write this out, at most 30% of people Hope if I can spell. So, at most means that P is less than or equal to 0.30, right? At most means 30 or less. So, remember, because this has a quality in it, this actually is our null hypothesis. We don't write it as an inequality, we write it as 0.30 equals 0.30, but this is our claim since it has our inequality symbol in it. A lot of our examples do not work with these kind of, I don't want to say trick inequalities, but a lot of them are more straightforward and like greater than or less than situations where we make our null hypothesis equal and we make our alternative whatever greater than or less than we were using. So because we're using less than or equal to, that means our alternative is greater than 0.30. All right, so now we're ready to run our test. We'll hit stat, go over to test. We're doing a 1 prop z test still. Our initial p-value was 0.30. Our x value is 38, our n value is 100, and then we're claiming that it is greater than that 0.3. So we get a z value of 1.746. We're testing against a significance level of 0.05, and we got a p-value of 0.040. So this p-value is lower than this critical value. So when the p is low, we reject our null hypothesis, which means we are rejecting our claim. So that in this case, when I reject the claim, I would say there is not enough evidence to support the claim. And then I just reiterate the claim here. That at most 30% of people okay. Great. All right, so that's our kind of intro or review, or that's our intro into our prop z test. Again, very similar to our prop z interval, but we're running the hypothesis testing to test if our claims are true or not. So the only last piece of information for this is, right, we just did 1 prop z tests, so that left-hand side where we only have one population. Now we're going to talk about a 2 population z-test when there's 2 populations that we're comparing to each other. It's very similar in structure, in conditions. It's just when we're running the test, we're going to select a different button and there's going to be a little more information to type in. So again, let's look at an example together, and I think that that will kind of help you solidify your understanding. So we're going to go back to that first example that I had us start at and then we skipped over really quickly. So that was on page 160. So if you'll go to page 160, we'll go ahead and look at that example together. So in a random sample of 250 freshmen, 45% said that they like their school. In a random sample of 320 seniors, 60% said they like their school. Test the claim that the proportion of seniors who like their school is higher than the proportion of freshmen. Use significance level of 0.05. Assume, I should spell assume correctly, assume the samples are independent and randomly selected. So for our variables, right, we have 2 proportions here. We have our freshman information and our senior information. So for freshmen, we have that our N value is 250 and 45% said they like their school. That's not your X value, right? That's your percent. So this is 0.45. said they like their school. If I want to find the x value, which I'm going to need, I'm going to go ahead and multiply n times p together. So 250 times 0.45 would give me 112.5. Your calculator does not like, in hypothesis testing, does not like decimals. So I'm going to round this to 113. So then for our seniors, we're going to look at the same thing. We had a sample of 320 seniors. 60% of them said they like their school. So if I want to find my value, I'm going to do n times p again. So here, 320 times 0.6 would give me 192 as my x value. So again, because we're looking at two separate groups of people, that means we're running a 2-prop z-test. We're looking at two proportions when we're running our z-test. We'll check the exact same conditions. We just have to check the conditions for both of our populations. So are they both a simple random sample? Does the n times p greater than 10 for both of them, etc.? So it's just a little bit more checking. I typically just check them right under, like side by side, right? Simple random sample, simple random sample. If I do n times p, which I've already done here, I got 113. That's definitely greater than or equal to 10. If I do n times p here, I got 192. That's definitely greater than or equal to 10. And then we got to do n times 1 minus p. So that would be 250 times 1 minus 0.45, which is 137.5 or 138. We're good there. And n times 1 minus p here would mean we're doing 321 minus 0.6, which would give me 128, also greater than or equal to 10. Then if I check that my n value is less than 1/10 of the population, it is safe to assume, right, that if we talked about all the freshmen, even in the United States, all the seniors in the United States, it's reasonable to assume there's more than 2,500 freshmen in the United States and 3,200 seniors. So we're going to be good on that condition. So then we're testing the claim that the proportion of seniors who like their school is higher than the proportion of freshmen. So this one is kind of our standard null and alternative hypothesis, right? We want that the proportion of seniors is greater than the proportion of freshmen. Remember, your null hypothesis is always equality, so our null hypothesis would be that they're equal if we make P1 freshmen and P2 seniors. And then if our seniors is higher, that means that we would expect P1 to be less than P2. And then this is here our claim, right? We're claiming that our amount of seniors who like school is greater than our amount of freshmen. All right, so we're ready to run our test. So again, it's all very similar to our normal 1 proportion z-test. The difference here is we're going to use 2 proportion z-test when we're putting it into our calculator. So starting with our x1 was 113. Again, your calculator will not like decimals, so make it round it up to a whole number. Our n value was 250. Our x2 was 192. N was 320. And our alternative hypothesis is that P1 is less than P2. So we'll go ahead and calculate that. So we get our z-score to be negative 3.515. We tested against a significance level of 0.5. And that p-value that we get is 2.196 e to the negative 4, which means we're moving this decimal 4 places to the left. So this is really 1, 2, 3, 3 zeros in front. So since our p-value is low, we reject our null hypothesis. So we're rejecting this, which tells us that there's enough evidence to support our claim since we rejected our null hypothesis. So there's sufficient evidence. And again, I labeled these conclusions, I state pretty much the same every time there's either not sufficient evidence or there is sufficient evidence to support the claim. Good. So hopefully looking at those examples was enough to kind of get you trying some on your own. So I'm going to go ahead and have you practice